All right, today we are diving into one of the most, and I mean this, one of the most beautiful ideas in all of math and physics, Stokes Theorem. At its heart, it's this incredible bridge between the huge, big picture stuff and all the tiny little details that make it happen. So let's get into it.
To really wrap our heads around this, let's start with a question you've probably seen in real life. Picture water swirling down a drain. You see that big, obvious rotation, right? The main vortex. But what if I told you that that one big motion is perfectly, and I mean perfectly, explained by adding up every single tiny, invisible swirl happening at every point inside the water? That's the exact kind of puzzle Stokes' theorem just solves. So, first things first. Let's talk about that big, observable rotation. How in the world do we actually measure the total amount of swirl that's happening along a boundary?
Okay. Imagine you've got some kind of invisible force field. Could be water flowing, could be the wind, maybe even a magnetic field. Now let's just draw a closed loop, a complete circle or square or whatever, right in the middle of it. What we want to know is, what's the total effect of that field as it pushes along our loop? Well, there's a mathematical tool for that, and it's called a line integral.
A line integral. You know, it sounds complicated, but it's really just asking a pretty simple question. As we walk all the way around this closed loop, how much is the field helping us move forward versus how much is it pushing back against us? We just add up that push or pull at every single tiny step. The final number we get is the total circulation. That's our big macroscopic swirl.
Okay, so we've got the big swirl around the edge figured out. Now, for a second, let's totally forget about that outer boundary. Let's zoom way in and look at what's happening at every single point on the surface inside that loop.
The idea here, and this is the key, is to imagine we could place a teeny tiny microscopic little paddle wheel at any point we want on that surface. Would it spin? You bet. How fast would it spin? And which way? This tendency to spin exists everywhere, at every single point, not just on the edge. And you guessed it, math has the perfect tool to measure this microscopic swirliness. It's called the curl, and you'll see it written as del cross F. The curl gives us a super precise description of the rotation that's happening at one single, infinitesimally small point. Now, what's so cool about the curl is that it's not just a number, it's a vector. That means it has a direction, which tells you the axis that our tiny paddle wheel is spinning around, kind of like its axle. And its length, its magnitude, tells you how intensely it's spinning. So yeah, it's the whole story of the local rotation in one neat package. So let's recap. We've got two totally different ideas on the table. We have the big circulation happening all the way around the outside boundary, and we have the tiny little swirls happening at every point on the surface inside. I think you can see where this is going. Let's put them right next to each other. Okay, look at this. On the left, you've got the line integral. That's our measure of the total flow around one single outer boundary. Then on the right, you have the surface integral, which is just our fancy way of saying, let's add up the curl, that microscopic swirl, over every last point on the surface. I mean, they look completely different, right? One is all about the edge, and the other is all about the inside.
And right here, this is the mic drop moment. This is Stokes' theorem. It says that these two calculations, the big one on the boundary and the sum of all the little ones on the inside, will always give you the exact same number. They're not just related, they are equal.
This just says it all perfectly. The big swirl is the sum of the little swirls. That giant overall behavior you see on the edge is nothing more than the grand total of all the tiny behaviors of every point on the inside. It's this fundamental, unbreakable link between the micro and the macro.
Okay, but why? I mean, how's that even possible? Well, the intuition behind it is actually surprisingly simple, and honestly, it's just beautiful. It all boils down to this really clever idea of cancellation.
So here's how you can think about it. First, just imagine we chop up our whole surface into a grid of teeny tiny little squares. Now, each one of those little squares has its own little circulation around its own little edge. But here's the magic trick. Wherever two squares touch, they share a wall. And the circulation on that shared wall is going in opposite directions for each square. So they perfectly cancel each other out. Every single internal wall just vanishes from the calculation. And what's the only thing left that doesn't get canceled? You got it, the grand outer boundary. It's brilliant.
Now, because of this deep connection, we get an incredibly powerful and practical consequence. It basically hands us a fantastic shortcut for solving problems that would otherwise be, well, a huge pain.
This is what we call surface independence. And what it means is, as long as you keep the boundary loop the same, it does not matter what the surface inside looks like. Seriously, it could be flat as a pancake, or bumpy, or stretched out like a big soap bubble. The total sum of all those little swirls inside will be identical.
So here's the amazing takeaway from that. Let's say someone asks you to do a really hard calculation over that complicated, wavy, parachute-shaped surface. Well, you don't have to. Thanks to Stokes' theorem, you can just throw that surface away and replace it with a dead simple flat disk, as long as it has the same boundary. And the answer will be exactly the same. It's like a mathematical superpower.
We've gone through the math, we've gone through the intuition, but I really want you to leave with the idea that this is so much bigger than just a clever math trick. This is a fundamental description of how our universe is actually put together.
Seriously? Stokes' theorem pops up over and over again in the fundamental laws of nature. It's a pattern the universe seems to love, this connection between local behavior and global phenomena.
You see it in electromagnetism, where it explains how a changing magnetic field creates a circulating electric field. That's the core principle behind every electric generator on the planet. You see it in fluid dynamics, where it connects the massive rotation of a hurricane to the sum of all the little vortices inside it. It's just a deep, unifying rule of the game.
And that kind of leaves us with one last big thought to chew on. Stokes' theorem shows us this absolutely beautiful relationship between an edge and its inside, between the whole and the sum of its parts. So the question is, where else do we see this? Where else in science, or maybe even in life, does this same profound pattern show up? Thanks for joining me.